Hello, this is Matti Poke from University of Oulu, Finland. This is our presentation for the IEEE VR 2020 conference. The title of our study is The Plausibility Paradox for Scaled-Down Users in Virtual Environments. Many of us have seen films, TV shows, or maybe even played some video games in which the characters have been artificially reduced in size. We've seen then how these characters interact with various things like matches, needles, Legos and such in their environment. Maybe we've seen how the characters are jumping off ledges or even swimming in puddles of water. However, what usually happens during these interactions is that things are not really behaving in a way that would be realistic on that scale. Instead, all the physical phenomena that we see takes place as if the characters were human-sized and the environment was enormous instead. For example, if you look at the picture there on the left, it is easy to imagine how that Lego character drops to the floor pretty instantaneously once the cat knocks it down. However, if that was a human character in a movie, like there on the right, we would probably see something resembling a human dropping from an enormous cliff in terms of acceleration and time of flight. In virtual reality, we can live through these kind of experiences ourselves. In fact, previous research has found that we humans are prone to interpret ourselves as normal-sized and the environment is scaled up when provided with some kind of illusion of being artificially scaled up or down. This is especially true if we see our own body or parts of it, or if we are experiencing a body ownership illusion, since previous research has found that humans tend to use their body, for example hands, as an important metric when judging mismatching size cues. So why should we care about these things? Well, there are actually many applications that allow us to experience the world scaled down. These applications include multi-scale collaborative virtual environments and even multi-scale collaboration through both augmented and virtual reality. Applications in the real world might include things such as robotic teleoperation in medical and other domains. In this study, we focused on reducing the user's size by an order of magnitude. This makes the user approximately doll-sized. The following are some examples of what we can directly manipulate in virtual reality when messing with user's size. Viewpoint height is maybe one of the most obvious things. When we get smaller, the viewpoint height goes down. When dealing with stereoscopic VR, the virtual interpupillary distance also changes. And that really quite heavily affects our perceptions of sizes and distances. If we have some kind of visualization of our body, we can also change that in size. Of course, we can also simulate strength and locomotion speed in relation to our size. Manipulating these properties in turn changes how we see things in our environment. Our perception of sizes and distances changes. Also, our perceived ability to act can change, like for example the perception of one's ability to move objects. The environment can also affect these perceptions. The presence or absence of familiar size cues can affect our perceptions, as well as the presence or absence of other people. What we're focusing in this study is the perception of physical phenomena. Especially we are focusing on what kind of phenomena the user are finding realistic or unrealistic. In terms of virtual reality research, this makes our study an experiment in which we are examining the plausibility illusion. However, we are leaving virtual humans out of the scope and are only focusing on the behavior of virtual objects and the matching of expectations. Our assumption was that realistic approximation of physics in small scales does not match the expectation of our research subjects. To study this, we chose two conditions which we would be comparing in a laboratory experiment. First, true physics, which is the realistic approximation of physics, and movie physics, taking inspiration from films mentioned earlier. And here are our hypotheses. For a scaled-down user, movie physics is more likely to feel realistic than true physics, and for a scaled-down user, movie physics is more likely to match users' expectations than true physics. We set up an experiment using a virtual environment that depicted the main hallway of our university campus building. Its dimensions were based on CAD models of the actual environment. We also took measurements of some nearby objects in the actual hallway and put models of them as props in the virtual environment to provide some size cues. We used Unreal Engine 4.22 for development. In both conditions, we gave subjects the illusion of being reduced in size by a factor of 10. In the true physics condition, we simply relied on Unreal Engine built-in NVIDIA physics engine to provide the correct physics simulation when we reduced the player character in size by a factor of 10. In movie physics, however, we enlarged the environment by a factor of 10 while keeping the player character human-sized. This way, both conditions looked the same, but were different in terms of physics simulation. To experiment with the physics condition, we gave the subjects the task to try dropping and throwing virtual pull tabs similar as found in soda cans, for example. Our tabs were roughly 3 centimeters lengthwise and a bit less than 2 centimeters in width. We placed the tabs on top of a book so that they were easier to pick up. We also placed a Coke can nearby for an additional size cue. We had 44 subjects, 23 females and 21 males. Subject ages ranged between 19 and 66, mean and median ages being 30 and 26 respectively. All subjects performed both conditions. The conditions were counterbalanced so that there was the same number of males and females starting with either true physics or movie physics conditions. We used the Oculus Rift S for our study. We used the Oculus setup to set the virtual IPD at 64.5 for males and 62.5 for females. Of course, in the true physics condition, this IPD was also scaled down by a factor of 10. Let's now take a look how the interaction task looked like in both conditions. As we can see in the true physics condition, the tabs fall to the ground rather fast. Also, they cannot be thrown very far due to the reduced velocity that the subjects could impart. The flight of the tabs was not based on any kind of simulated muscle strength, but simply due to the velocity of the virtual hands when throwing. Velocity was smaller because actual hand movements were scaled down into very small doll-sized hand movements. However, in the movie physics condition, the physics are wrong but behave in a way that we are more used to. It takes longer for the tabs to fall down, they can be thrown very far away, and they are also bouncing nicely. After the subject performed both conditions, we asked them to fill a bunch of questionnaires. At first, they were faced with 2 forced choice questions. First, thinking back how the pull tabs were behaving in the experiment, which felt more realistic, like what would happen in the real world if you had been shrunk down, the first or the second time. Thinking back how the pull tabs were behaving in the experiment, which match your expectations, similar to what would happen in the real world if you had been shrunk down the first time or the second time. We also asked the subject to fill in why they felt the way they did. After the forced choice questions, the subjects responded to a 7-scale Likert questionnaire, asking about various properties regarding the flight of the pull tabs, like the falling speed of the pull tabs, the speed of pull tabs when thrown, the distance when thrown, the way the pull tabs were bouncing when thrown, and the impact of gravity on the pull tabs. After that, the subjects also responded to the Slater use of Steed presence questionnaire and finally filled in background information for asking for age, educational background, and their experience with VR and video games. And now we'll look at the results. According to the responses to the forced choice questions, almost 3 out of 4 subjects considered that the movie physics condition was the realistic one. Also, 9 out of 10 thought that the movie physics matched their expectations more. Also, according to the responses to the open-ended questions that were next to the forced choice questions, the preferences were mostly because of the physics conditions. For example, gravity feels more natural and such. There were 6 responses to the first open-ended question that were unrelated to physics. 5 of these were related to interactional learning. For example, I liked the second time better because I knew how to use the controllers. All of these were subjects starting with the true physics condition. The responses to the Likert questionnaires also indicated preferences towards the movie physics. Inspecting the responses to the bipolar questions L1, L2, and L3, we can see that all the responses regarding movie physics are gravitating around 4, meaning that the movie physics condition was perceived more realistic in terms of these types of tab behavior. The responses to L1 and L3 are where we expect them to be, at the unrealistic ends of the spectrum. However, L2 is an exception. We can see that the median answer is 4 there as well. However, the distribution of responses is all over the place compared to the movie physics condition. Questions L4 and L5 were unipolar, meaning that the responses closer to 7 indicate realism. In these responses, the movie physics is clearly perceived more realistic. Following the example of an earlier plausibility study by Scarbez and collaborators, we divided the subjects into groups of low presence and high presence to see if these groups had any differences in their responses. However, we did not find high or low presence having any effect on the responses to the first false choice question. We also looked into background and actual SUS scores as predictors. We transformed responses to educational background into 2 roughly similar sized groups: natural sciences and engineering, and social sciences. We also looked at the effects of gender, age, VR experience, and gaming experience. We did not find any of these variables to have any predictive capabilities either. One thing that caught our attention was how several subjects commented on feeling of heaviness regarding the tabs, as in the tabs felt more heavy in either condition. We're not sure if this just means that the tabs seemed heavier to the subjects in one or another condition, or if there was actually some kind of pseudo-haptic phenomenon going on. Also, some subjects were contemplating on how much muscle strength one should or should not have in order to throw the tabs when small. For some reason, these thoughts regarding strength appeared only with the Finnish-speaking subjects. In overall, the results implied that we did find a paradox concerning plausibility for scaled-down users in virtual environments that contain physically simulated interactions. The responses to the forced choice questions implied that the realistic approximation of physics was not seen realistic and did not match the subject's expectations. The responses to the open-ended questions and the Likert questionnaires support this finding. We believe that this finding might have implications for example, robotic teleoperation and VR, in which realistic simulation of physics is relevant in small-scale operations. This could be, for example, a maintenance robot moving in small spaces, or an MCVE involved in the design of microelectromechanical systems, for example. We also believe that the further the scale goes from our regular human scale, the more these physics peculiarities are amplified. Static electricity comes into play, frictions, fluid dynamics, van der Waals forces. All these things don't really affect us in normal scales, however, they become more significant the smaller we get. Our study had the following limitations. Responses to L2 were not consistent with the other findings. In here, the median responses for true physics was the same as for movie physics, but the distribution of the responses was very different. We believe that this was because of a poor wording of the question L2, the speed of the pop tabs when thrown. Some subjects thought that they had problems throwing because they had not yet learned how to use the controllers. This is problematic because we couldn't really have had any kind of training session, because this would have primed the subjects on how the physics should behave in VR. The experimental apparatus contained some limitations as well. There were a couple of physics bugs causing some cases where the tabs were behaving wrong, and there were minor lighting issues. There were also some cases when the subject didn't really pay attention to the pop tabs, and that might have affected their responses. In the future, we can avoid this by just giving better instructions. In conclusion, this study identified a new phenomenon. When users interact with simulated objects in virtual environments where the user is much smaller than usual, there is a mismatch between the object physics that they expect and the object physics that would be correct at that scale. We argue that our findings have implications for many virtual reality and telepresence applications involving operation with simulated or physical objects in small scales. In the future, we want to take a look at different scales as well. With this work, we also only focused on a single physical phenomenon with a single very simple task, but in the future we want to take a look at other type of interactions as well, and how they are affected by different physical phenomena. Also, we want to investigate how the body scaling effect affects the perception of physics. Thank you for your attention.